Almost all modern power electronic circuits contain at least one switching device. This is typically some form of transistor. We turn this switch on and off very quickly to control the flow of current. In theory, there should be zero losses in our switch, as it's always either completely off or completely on. Unfortunately, this is not the case. There are some resistive or conduction losses when the switch is on, and some energy is also lost every time we switch our device, the switching loss. This is what we'll be focusing on today, how to measure it and how to minimize it. We can do all of this with a single, fairly simple test, known as a double pulse test. We're going to start by taking a quick look at the circuit required, before diving into the results to show how useful and insightful double pulse testing can be, and then finally taking a look at the actual hardware setup I used to get the data. Speaking of hardware, the boards I've used for this video are from JLCPCB, who provide easy, affordable and reliable PCBs and assembly for over 6 million engineers around the world. This half-bridge board uses complex interleaved high-voltage layers to minimize inductance, and this requires the highest quality of PCB to prevent dielectric breakdown between neighbouring layers. Of course, I don't have to worry about quality from JLCPCB, as they use only the highest quality materials in their stack-ups. To order from JLCPCB, simply drag and drop your Gerber file onto their website for an instant quote, and the ability to select from a plethora of nice options, including ENIG, gold plating, and beefy 2-ounce copper. JLCPCB also offer rapid shipping, allowing me to receive my boards here in the UK within a week of ordering, which I find very impressive. So for your next project, make sure to check out JLCPCB using the link in the video description. Right, now let's take a look at the simple circuit we need to do a double pulse test. First off, we need our device under test, or DUT. This is the switching device we want to characterise, in my case a 750 volt silicon carbide MOSFET. To get the data we want, we must measure both the voltage across and current through this device, the latter of which can be quite challenging, and we'll take a look at this in more detail later on. Next, we need an inductor in series. This is to regulate our current. When we turn the switch on, the inductor will have the full DC supply voltage across it, and its current will rise according to dIdt equals V over L, a slight rearrangement of the standard inductor voltage equation, V equals L dIdt. We can use this equation to work out how long our first pulse needs to be. For example, if I had a 100 volt supply voltage and an inductance of 50 microhenry, then the current would increase by 2 amps for every microsecond the switch was on. Once the current had reached the level we want to test at, we simply turn the switch off. However, if we did that with the circuit as it is currently, all the energy built up in the inductor will be dumped into our switch, resulting in a tremendous voltage and instant destruction. This is far from ideal, so to prevent this we need to add in one more component, a freewheeling diode. This gives a path for the inductor's current to take when the switch turns off, and it will continue to circulate around this path until we turn our switch back on at the start of the second pulse. This means we now have both turn off and turn on waveforms for our chosen current level, and all that's left to do is turn off our switch one last time. Double pulse testing is often used to characterise half bridges in power converters like automotive traction inverters, and in this case there's no need for the external freewheeling diode, as the switches will already contain some form of diode. This is the case for the half bridge circuit I'll be using in this demonstration. Now that we understand the circuit and its operation, let's take a look at some of the data we're able to extract from the waveforms, starting with the thing we're trying to minimize, the switching loss, or more specifically, the switching energy. The switching energy is a result of both voltage and current being present on the device during switching. We can see this clearly when we multiply the two waveforms together, which reveals that our little MOSFET is having to deal with around 25 kilowatts of instantaneous power. That's more power than the supply to my house can handle, but thankfully our MOSFET can easily survive this, as it only occurs for around 20 nanoseconds. This happens every time the switch turns on or off, and we can calculate the amount of energy lost from these waveforms. We'll look at the specifics of how to do this later on, but for now let's take a look at an example of the incredible insight it can offer. Here you can see we've got 5 curves for the DC voltages between 200 and 400 volts in steps of 50. These are the voltages at which I carried out my tests, but of course you can do double pulse testing at any voltage you like. Our x-axis is showing the current that was switched, ranging from 6 amps to a little over 60, and the y-axis shows the switching energy, the loss we have every time we switch our device, in microjoules. While a few hundred microjoules may seem insignificant, many converters operate at well over 100 kHz, meaning this energy is repeatedly lost, hundreds of thousands of times per second, which would result in tens of watts of overall switching loss, which is significant. These curves are specifically for turn-on energy, We can also calculate the turn-off energy, which in this case is quite a bit lower. As you'd expect, the losses increase with both voltage and current, and if either of these can be reduced, the switching losses will also come down. We can also see that the lower voltage curves contain points at lower currents. This is because I kept the same pulse widths when I changed to the DC voltage, meaning the current increased at a different rate, but for the same amount of time. Ideally, you'd want to extend the pulse width for lower voltages, so that the switching current is always the same, but I'm lazy, so I didn't do that. Now, while the switching energy is the thing we set out to improve, there are a few other things we need to measure in order to minimise it, while keeping our circuit safe and reliable. The most critical of these is the voltage overshoot that occurs when we turn the device off, which we can clearly see here in the voltage waveform. This is caused by the rapid change in current and the inductance of the switching loop. Don't worry, we'll take a proper look at both of these things shortly. We can see that the overshoot is pretty much proportional to the switching current, and isn't really affected by the DC voltage, with a maximum here of about 125 volts when we switch at roughly 65 amps. When we turn off, this voltage appears across the switch in addition to the DC voltage, and we can see this by looking at the peak voltage rather than the overshoot. This peak voltage is the number one determining factor for how fast we can switch. Faster switching will reduce the switching losses, but will also increase the overshoot and peak voltage. If the peak voltage gets too close to the switching device's breakdown voltage, it will lead to premature failure, which we don't want. The switching is sped up or slowed down by decreasing or increasing the gate resistance respectively. Here I've repeated the tests with a lower 2 ohm gate resistance, and we can clearly see our overshoot has increased. We need to do a bit of trial and error to find the lowest gate resistance at which our overshoot is within a safe margin of the device breakdown, and this will give us the lowest possible switching losses for the given system. Now, while this overshoot occurs when we turn off, it's really important to be aware of the other overshoot, which happens when we turn on. With a basic double pulse test setup like I have, we can't see this overshoot because it doesn't actually occur on this device, but rather the opposite switching device, in my case the high side MOSFET. Ideally, one would also measure the voltage across that device to ensure that turn on is also not too fast. Sometimes this means that one of the switching edges will have to be much slower than it could be, in order to keep the overshoot safe on the other. We can get around this by adding a second gate resistor with a series diode, so in one direction current passes through only a single gate resistor, and in the other it will pass through both in parallel, reducing the effective resistance and speeding up only that switching edge. Fancy gate drivers even have separate turn on and turn off outputs, eliminating the need for the diode. Let's now take a look at how much the switching energy has reduced with our lower gate resistance. Our turn-off energy has gone down by about 16%, which is not insignificant. However, our turn-on energy has more than halved, with a reduction of 60%. That's fantastic. This happens because the time over which the switch has both voltage and current present is reduced, as you can see here. There are still a few more interesting nuggets of knowledge we can extract from our double pulse waveforms, for example the rate of change of voltage, or dVdt. How fast the voltage changes is really important to know, because it can be the source of many problems, mostly resulting from current that flows through any parasitic capacitances in the circuit, determined by I equals C dVdt. This tells us that, for a given capacitance, a pulse of current will flow whenever the voltage across that capacitance changes rapidly, and these unwanted currents have been the cause of many headaches for many years, as they can seriously disrupt whatever circuitry they flow through, and can even damage things like transformers and motors by breaking down their insulation. Because of this, switching will sometimes have to be further slowed down to keep the rest of the system happy by lowering the dVdt, and this is something worth trying if you're experiencing noise problems when switching. Here we can see the change in dVdt between the 2 ohm and 6 ohm gate resistances, with a clear increase at faster switching speed. If you have any components that will experience high dVdt, make sure to check their Common Mode Transient Immunity, or CMTI. For example, these Murata DC to DC converters I've used on my gate driver boards are rated for at least 200 kV per microsecond, whereas many similar DC to DC converters have no rating at all and weren't designed for such applications. We also have the same thing for current, dIdt, the main impact of which is the overshoot we've already looked at. But this can also cause EMI issues due to the rapidly changing magnetic field, which may require additional filtering or shielding to comply with regulations. We can see that, like the overshoot it causes, this isn't really affected by voltage at all, which makes sense because it's the current. The last thing we're going to look at is my favourite, and it's the thing relating the overshoot and the dIdt, the loop inductance. This is something you can't really measure directly because opening up the circuit to take the measurement would disrupt the inductance significantly. Usually you'd have to resort to simulations in software like ANSYS to estimate the loop inductance of a system, but you can also do something rather clever using data from the double pulse test. We know that the overshoot is determined by the equation V equals L didt, and we know both V and didt, so we can just rearrange this slightly to get L equals V divided by didt, which will give a pretty good approximation of the overall loop inductance, as we can see here. To extract all of these values from the double pulse waveforms, we need good definitions for them, for which I use these handy figures kindly provided by Wolfspeed in some of their device datasheets. These show how to calculate all the values I've shown today, and more, such as rise time and reverse recovery current. Let's take a quick look at how I calculated the values I've shown, starting with the most complicated, the switching energy. The figure tells us that the turn-off energy is the product of voltage and current, so the power, integrated between the time at which the drain source voltage exceeds 10% of the DC voltage and the time at which the source current drops below 10% of its original value. Here you can see both of those points marked on the voltage and current waveforms. And here's the power waveform with the area defined by those 2 points shaded in. This area is the switching energy. We can see the definition is pretty much identical for turn on, except voltage and current have swapped. For dVdt and didt, we're told to find the peak rate of change for a sliding 5 nanosecond window, which sounds a bit complicated, but it's actually fairly simple to implement. We just need to apply a moving average to our differentiated waveform, giving the mean of however many samples are taken in 5 nanoseconds, and then find the maximum value in that averaged waveform. The Rigol oscilloscope I've used has a pretty low 2-channel sample rate of just 500 megasample per second, meaning it takes 2.5 samples every 5 nanoseconds, which I rounded up to 3. One thing that isn't mentioned here is the loop inductance approximation, so I'll just quickly go into a little more detail on how I've done that. I did lie a little bit earlier when I said I used the turn-off overshoot, because I actually used this weird little dip in voltage that occurs while the switch is turning on. This is caused by the same phenomenon as the overshoot, except this time the rapid change in current is in the opposite direction, so instead of adding to the DC voltage, it subtracts from it. The approximation of the loop inductance is more accurate if you can use this voltage droop rather than the overshoot, because the didt at turn on is much more stable. I've written a script in MATLAB that will eat up all the CSVs from the scope and spit out all the parameters from each double pulse test, which is the data I've shown in all these lovely plots. This could of course be done in countless other programming languages such as Python, which has the added benefit of being free. Now it's time to take a look at the physical setup, and let's start with the boards I've designed for this demonstration. First of all, we have the half-bridge board, which contains a pair of Wolfspeed silicon carbide MOSFETs. There is also a large 45 microfarad 500 volt film capacitor, representing the DC link capacitor of a high voltage converter. I've added a small 1 microfarad Cerilink capacitor closer to the MOSFETs to act as local decoupling and reduce the effective loop inductance at high frequencies, which will in turn reduce overshoots and oscillations. Next to each MOSFET there is a small multi-layer ceramic capacitor between gate and source pins to dampen any oscillations that may result from the longer than ideal gate drive path. Speaking of which, there is a 2-pin header next to each MOSFET for the gate driver to plug into. Finally, there are these beefy terminals for positive and negative DC input, as well as the output of the half-bridge where we'll connect our inductor. The second board I've made is the gate driver board, which is removable so it can be easily swapped out to try different gate resistor values. These contain an Infineon dual gate drive IC, which is powered through the Murata DC-to-DC converter I mentioned earlier. There's a small silicon carbide Schottky diode on the back of the board for bootstrap operation, though this wasn't used in this video. Finally, there is a pair of gate resistors for each MOSFET in the series diode configuration shown earlier. The first part of the setup we need to sort out is the inductor, and for this we can't use any old inductor because hysteresis in the core will disrupt the results, and more importantly there's the chance of saturation, which we really don't want. To get around this, we need to use an inductor that cannot saturate, an air core inductor. While this may sound rather exotic, it's just a coil of wire. Here's one I made earlier. Next, we need to set up our measurement of voltage and current. Voltage is fairly easy, as long as you remember to consider the rating of your probe and any ground loops if it's not isolated. As I'm running at voltages in excess of 400 volts, I'm going to be using a high voltage differential probe, specifically this nice compact USB-C powered one from Mixig, kindly loaned to me by Telonic. It's important to connect this as close as possible to the device die to see the most accurate voltage. For this reason, I've used the Kelvin source connection of the MOSFET. I hinted earlier that measuring device current is not trivial, and indeed trivial it is not. We need a non-destructive, non-intrusive method to measure the current, which is challenging enough with through-hole devices, but seems like an impossibility with such small surface mount ones. Well, that would probably be the case if it wasn't for this very clever piece of kit called a Rogowski coil. A Rogowski coil is essentially a piece of wire wrapped around itself. When put into a loop like this, it will produce a voltage proportional to the rate of change of the magnetic field or current passing through it. This can then be integrated to provide the actual current, which is what goes on inside this box. This particular Rogowski coil is so thin it will actually fit through the legs of these surface mount MOSFETs. How cool is that? To run these tests at up to 400 volts, I needed a high voltage power supply, which was again kindly loaned by Telonic. This compact 650 volt Kikasui unit is really nice. It has a maximum current of 1.85 amps and a power limit of 400 watts, perfect for double pulse testing. Finally, I needed to generate a simple logic level double pulse waveform to control the gate driver. While any decent arbitrary waveform generator will be capable of producing such a waveform, I don't have any arbitrary waveform generator, so I wrote some code for this PIC32 dev board to output a pair of variable width pulses, making use of timers and interrupts. And that's it. We can now double pulse test. I hope this video was helpful for anyone looking to do some double pulse testing, and was insightful for anyone who hadn't heard of it before. If you've got any lingering questions, just pop them down below, and I'll try my best to answer them. With that, thank you very much for watching. Bye!